Hello, and thanks for listening in. The point particle theory of the classical electron follows beginning with the set of Lienard Wiechert potentials, which were derived near the beginning of the 20th century. These potentials can be differentiated for the most general motions of the electron to determine the antisymmetric field strength tensor. Now, suppose we introduce a scalar field phi and add its foregradient to the Lienard Wiechert potentials. Taking derivatives again shows that the field strength tensor is immune to the presence of the scalar field. This is gauge invariance applied to the fields of the electron. Now suppose we pick a very special scalar field phi is equal to minus e log rho. Calculating the foregradient of this field, we see that the first term annihilates the Lienard Wiechert potentials. The remaining terms are a new set of potentials, and we note that the first term does not depend on particle accelerations, but the second term does. Accordingly, let's write the new potentials as A nu is equal to A nu sub v plus A nu sub a, and let's refer to them as vacuum gauge potentials. Explicit forms of the velocity and acceleration potentials are shown here and have some interesting properties. First, both point along the light cone from the retarded position of the particle to the present time field point. In fact, the acceleration term is proportional to the velocity term. Second, the factor of c squared in the denominator of the acceleration potentials implies that they are a very small correction to the velocity potentials, unless particle accelerations are extremely large. Next, we can differentiate both sets of potentials and show that the velocity potentials will only give you the particle velocity fields, while the acceleration potentials will only give you the acceleration fields. In other words, the vacuum gauge allows the velocity and acceleration fields to be addressed as independent theories. Having derived the vacuum gauge potentials, the next question is this: what can you do with vacuum gauge potentials which cannot be done with Lienard Wiechert potentials? First, vacuum gauge potentials point radially from the source and are therefore appropriate for the description of a single charged particle. In connection with this, you can use vacuum gauge potentials in computer programming to determine potentials and fields of complex distributions of charge by adding up the fields one particle at a time. Next, vacuum gauge potentials allow you to insert radiating longitudinal modes into electron velocity fields. You don't need to add these radiative modes since they violate energy conservation, but at least the vacuum gauge gives you the option to do so. Next, vacuum gauge potentials allow for simple procedures to quantize the particle. Specifically, in another video, we show how to calculate Dirac spin-ors beginning with the velocity potentials and the velocity fields. Finally, vacuum gauge potentials allow more efficient calculations for many problems in classical electrodynamics. For example, suppose you are writing a book on multipole radiation fields. Vacuum gauge electrodynamics lets you work directly with the acceleration fields without ever having to address the velocity fields. To close our video, let's calculate electric dipole radiation fields of a single electron using vacuum gauge potentials. To do this, we write the acceleration field strength tensor and determine simple formulas for electric and magnetic acceleration fields. Now suppose our electron undergoes small oscillations on the z-axis of a coordinate system. To determine the acceleration fields of this particle, we only need the rest frame vacuum gauge potentials, which we show here. This means we can generate the appropriate acceleration fields in equation 1 simply by evaluating components of the particle acceleration. The equation of motion for the oscillating electron is shown here, where t sub r is the retarded time, and this formula can be differentiated to determine particle accelerations. The dipole fields will then follow by combining the potentials and the acceleration components together according to equation 1. This calculation can be compared with Griffith's, which arrives at this result beginning with two metal spheres connected by a wire and requires several pages of approximations to get the result. While we like Griffith's book, we also like simple results offered by the vacuum gauge. Finally, if you are interested in downloading copies of research papers on vacuum gauge electrodynamics, all you need to do is type in the internet address shown here for the GitHub where they are stored. As of April 21st, 2024, there are 5 available PDF files which can be downloaded by first clicking on them and then selecting the download button in the upper right. For reference, the author's CV can also be viewed on the GitHub. Thanks again for listening in and have a great day.